Swayam Prabha. Digital India. Educated India.
Good morning everybody. We are now studying the response of non-premixed flame to flow perturbation. We already studied premixed flame response. Now we are studying this non-premixed flame or diffusion flame. We are kind of looking at the classical diffusion flame and trying to follow the analytical approach, except the difference is that we are looking at the unsteady equation, and the equation that we are trying to solve is the advection diffusion equation, which is and to obtain the steady part we have to drop the first term and we have to get a steady solution or the steady base flow, and then on top of it we can linearize this equation and get a perturbation equation. Of course the equation is linear in Z, so it's we do not have to drop anything, but the thing is if you separate into a steady and a steady base flow and a perturbation equation we can get neat analytical solution. So that is a big advantage, and before we continue we emphasize that we identified two time scales or two non-dimensional numbers associated with this thing. One is Peclet number, which is ux comma 0 w2 over d. So this is kind of like Reynolds number convection over diffusion, but here we are Reynolds number deals with momentum transport, here we are looking at mass transport. Similarly we have Strouhal number, so W2 over ux naught denotes one time scale, 1 over f denotes another time scale. So this is like a time scale of the flow, 1 over f is like the time scale associated with the unsteadiness, and so that is the other. So we say that here in this inner block Z is 1, here Z is 0, right, and then we have a center line, so we have to have symmetry. So let us write this Z equal to 1 here, Z equal to 0 here, and at the center line dou Z by dou I should be 0 here also, and at infinity we should tend to some finite number and solution should not blow up and so on. So this is what we need to solve. I hope this much is clear to everybody from last time. Are there any questions? I will pause for 1 minute to answer any questions. Okay, so our objective is now twofold. First is to get the solution for the steady base flow, and once we do that we will try to get the solution for the unsteady part. Okay. And so here our objective is when we studied the G equation and the premixed flame formulation we could directly track the flame, but then the value of G itself was really of no major physical significance in that particular formulation. Here whereas Z is a very physical quantity, it is x minus y, and x and y are very physical quantities dealing with the mass fraction of fuel and oxidizer. So we are actually solving for the entire Z field, and then we can track the flame which is happening at this Z stoichiometry. So wherever is the stoichiometry we call that the flame sheet, and so once we put that in and then we get the equation for the flame surface. That much is clear, right? So let us start first with the steady part. Governing equation was, so we are solving for steady solution. will following low events convection, comma 0 means base flow or steady flow. So let us do some kind of non-dimensionalization to keep things simple, so that the solution will come out nicely. So rather than copy the solution, please work out the problem along with me and let me know if there are any mistakes. So we non-dimensionalize y with this slot width W2 and x with x we are non-dimensionalizing with this. So now if you look, we will get so x by, so you should get I hope this much is straightforward. So we can club what was our definition of Peclet number? It is ux naught W2. So there was W2 squared. So ux naught W2 over d. So this would be on over Peclet number, right? Peclet number. So we are left with there is a u and a W2. So I divide throughout by d. So comma 0 over d. There is a W2 here. I multiplied throughout by W2 square. So this will come to top. This is also, this is like Peclet number, right? So I have divided by W, divided by D and multiplied by W2. So all I have here is dou squared by dou y star squared plus I took out one d, so I have t squared left, and I removed W2 squared, so I have so this is Peclet number, and this is 1 over p squared. Okay, so this should cancel with this, right? This and this are so cancel. Huh? Where? Here?
Last one.
Sorry.
That should be ux naught.
Yeah. This ux naught squared here. Thank you. So this will cancel. You have 1 by Peclet squared here. This as a coefficient of 1. So we get a very neat equation. So although for a moment the equation looked like it was going to be a mess, but I think if you are doing it right, all things will combine together and cancel. Now we need to solve for this. How would you solve for this? So we use variables. The meaning of separation of variables is when you have a function of, so here everything on the left hand side is a function of x, everything on the right hand side is a function of y. So if you can manage to write it that way, then each of them should separately be equal to constant. So there is a good chance that this would work and we should be able to write the left. At the moment we do not know what is z0, but if we say that z0 equal to fy of y star into fx of x star and substitute it here, what you would get is fy of y star do square fx of x star divided by dou x star minus 1 over Peclet squared f y of y star dou squared z0 by equal to f x of x star into dou squared fy of, I hope this is right, please let me know. So these are kind of the typical equations you would encounter in studying combustion. So it is good that we are going through this exercise, and separation of variables is a very simple solution technique, but there are many instances where we can use it, so it is a good practice for you. So what we do next is to divide throughout by fy and f of x, divide by x star, and then we should be able to separate out, or if we do then we have success, if we do not, separation of variables is not working. So if we divide this, what you will get is 1 over f of x x star. Actually I can write d instead of dou because each is a function of only that variable, so I do not need to write partial derivative, it is simple derivative. Okay. So this particular part, yeah, right, yeah, thank you. Yeah. So the left hand side, yes. So the left hand side is a function of x, this part x star actually, and this is a function of y star. So if a function of x star equal to a function of y star, then both functions should be equal to a constant. So we then say this is equal to minus kn squared. Minus sign is simply for convenience there is no need to put it, but I mean just style, I mean you can put the other one and you will get the same result. Z naught equal to Fy of y star Fx of x star. Okay, so let us clarify this. So d z naught by d x star, right, x star equal to Fy of y star d Fx by dx d squared z naught by dx star squared equal to d by dx star of f of y star d of x star over dx. So as far as differentiation with x is concerned, this is a constant, so it just comes out, this is equal to Fy of y star d squared Fx of x star over star square. So I hope it's clear. Okay.
So Kn is it wave number or it's simply a constant?
It's a constant. We can it is some kind of wave number, but it is not the acoustic wave number, but it's some other kind of wave number. It's like a, of course here it's just a constant that is appearing, but it's eigenvalue basically. So we will have to write this. So lot of Kns can satisfy. So based on the boundary condition, we have to sort out or find out what Kn is there, and then we will. So if there are several Kns, then this is a linear solution. So we will have to write the function as summation of all these functions over all the Kns that are possible. So if you write minus Kn squared, so if you bring it over here, you will get d squared f over dy squared plus Kn squared f equal to 0. So that will say that f is like sine. Suppose I did not put minus, then I would get exponential, but sine, cosine and exponential, they are interchangeable. So depending on what actual boundary condition you put, that decides the sign of this, but here knowing, since I have worked it out, I know the answer, so I know that it will be a minus times some positive number. Okay, so it's in some sense you work through one way, even if you do the wrong thing, at the end of it you know that you can swap it, but then to keep things nicely you do this. So that is the advantage of doing things second time. So let us take a look at this part, the right side of this equation. I have reserved C1 and C2 for x, but since y is simpler, I am writing that first. Let us kind of box this solution. So we do not know the constants, we do not know the Kns, but there may be many Kns that satisfy, and then we will have to add all the solutions, because in a linear theory all the solutions can be superposed, but what you superpose depends on what boundary condition you use. That is the sum and substance of what you asked. So next part would be d squared f of x star sorry minus 1 over p squared dfx. So it is all function of x star, but I think by now it is clear. So this is our function of x star part. How would you solve this? I think we can guess that the solution is of the order of a e power mx. So let us guess solution of form e power mx. So, then what would you get? M minus 1 over p squared. I made a mistake here. This is okay? Yeah. Equal to minus kn squared. So, just writing it as in nice quadratic form. So, m equal to minus 1 plus or minus root of b squared minus 4 ac. So, 1 plus 4 kn squared over p squared, right, divided by I hope this is right. So, this we must be able to write this as p squared minus or plus root of p power 4 plus 4 p squared. So, let us call the let us call this equal to beta beta minus x and beta plus x. So, p plus square root of p power 4 plus 4 p squared kn squared, we will call that beta x plus. When we say p minus square root of p power 4 plus 4 p squared kn squared over 2, that we call it beta minus. So, then we can write the solution as so this is our solution, and our z is, if you look, is product of fx and fy. So, if you take the product of these two, we should be able to get the solution. Now, we have to apply the boundary conditions, and we will apply symmetry about y equal to 0. So, that will say that dfy over dx should be 0, because the slope should be 0, only then you will have a symmetric part, right. If you have a profile which comes like this, which is symmetric, then the slope should be 0 here. So, what would this give? So, let us differentiate. This will give kn C3 cos kny star minus C4 sin kny star. So, if you put y equal, this should be equal to 0. So, if you put y equal to 0, cos 0 will be 1, right. So, this k. So, C3 into 1 minus C4 into 0 equal to 0, which will give C3 equal to 0, fantastic. So, that has simplified our solution quite a lot. And so, we can write here now Fy equal to C4 cos Kn y star. So our solution is in terms of y star. That means what was y star? Y by W2. So we have to remember so next boundary condition is we have this is the wall, there should not be any diffusion through the wall. So dz over dy should be 0 here. So the wall is, so once we enforce W1, y equal to W1, y equal to minus W1 will automatically be enforced because we already enforced the symmetry. So this is a solution C4 cos Kn into y star was y by W2, this would be W1 by W2. Equal to 0. So this should give Kn, sorry, should say sign because the condition is on dz by dy, right. So when this is y, fy, dfy by dy will be like sign. So this is the answer to what you had asked, what are those Kns. Now they are being determined, these are the only Kns, that is n pi times W2 over W1, these are the only Kns that can satisfy the boundary condition. So the solution will consist of several Kns, one will be pi times W2 by W1, second would be 2 pi times W2 by W1 and so on and so forth. Now they will all have a coefficient in front that will have to be determined from the next boundary condition. Yes, yeah, I think natural frequency is a very specific term used for wave equation and solution to that. So this would be eigenvalue, that is a more general term. So Kns are the eigenvalues. Eigen comes from the German word on own or unique, something like that. So it's very similar to natural frequencies, but we are not solving a string vibration problem, so it's not exactly natural frequency, but something like that actually. Now we have to look at, let's take a look at fx star. So what happens to this term as we go downstream? This C2 exp beta plus x star. Beta plus means that's a positive number, that's all it means. It will keep on increasing, unbounded. We cannot let that happen, we cannot let this term blow out, so C2 is 0. So let's write this C2 equals 0 so that the solution remains bounded in x star. So we just have this term multiplying this term, okay, C1 e power beta minus x times C4 cos k n y star, okay, that's all. So since Kn takes infinite values, well that's, there is no upper bound on what is n and all that. So the solution to Z0 is an infinite sum over all integer values of n with coefficients, some kind of coefficients which are like this C1 times C4. So these coefficients, and we are adding n number of them, so they have to be solved using the boundary condition at the inlet plane. Okay, so it's clear, right? So how do you do this? So e power 0 would be 1, right? So we put our x equal to 0 here. So our solution is equal to Fy comma inflow of y star. So let's multiply both sides by cos kn y star and integrate. Okay. So this would be 1, this would be 0, so we can drop that, right? So you should get, we will look at the right hand side, so this would be 1 over kn sin kn. Is that okay? Let me know if this is not what you get. So on the left hand side we will do this integration, so you will get Bn times integral 0 to W1 over W2. This to integrate we will say it is 1 plus cos 2 ky star over 2 dy star. So just to write the final result, you will get okay. So this term becomes half, this will become sine, and then you can do the further simplification and get this, just try it out. And use this value of kn. Okay. So this term will drop and you will get this. So now we need to get B naught. So B naught we just we don't multiply anything, we just we just integrate that equation. So we have to find B naught. So this is our equation. So, we just integrate this. This W by 2 by W2 is nothing but 1. So, we know that K n equal to n pi W2 by W1. So, we use n equal to 0, that is what is of interest. So, 0 to W1 over W2 B naught dy star equal to integral 0 to 1, because this is W2 by W2, and this would be 1 here, this thing has a value of 1 in the fuel slot, this has a value 0 for Z. So, you will get 1 into dy star. So, B naught y star 0 to W1 over W2 equal to 1. So, y star is the upper limit is W1 over W2, lower limit is 0. So, you will get B naught W1 over W2 equal to 1, or B naught equal to W2 over W1. Okay. So, we will write the solution. This is what I should get. We are taking the beta minus solution. So, this is the full solution. We will fix that part next class. Now, want to look at what happens when Peclet number is large. Okay, I will just wait for you to look at this. I hope this is all right. Then we can simplify this expression. So, this term inside the bracket, it will become P E squared into 1 minus 1 plus n pi W2 over W1 whole squared divided by P squared over half. So, this would be P squared into 1 minus 1 minus So, when Peclet number is large, we can simplify it as this particular term. So, therefore, our full solution So this is the solution for the steady part of the Z function. Huh? Yeah. Thank you. And remember an equal to n pi. So wherever this term comes, we replace that by an, just for being simple. Thank you. So in the next part, what we have to do is we take the perturbation equation, then we force that equation with a velocity fluctuation which goes like cos omega t or sin omega t, and then we have to write the solution for that for a given u prime equal to some epsilon cos omega t. So what we have to do is to split the solution into a homogeneous solution and a particular solution, find each of them and then add them and find the coefficients using the boundary condition. So that is what we will do on the next class. We will stop here for the time being. Thank you.